We have seen that the SPI protocol defines a master and a slave, and each one of them has its own controller. We will only focus on designing a master controller for the SPI master because it's a little bit more difficult than the slave because it involves generating the clock and defining the different modes. The slave is simpler and generally speaking is ready for us because it's already implemented in the peripheral we're trying to communicate with. So in our design, we'll explain it using mode 0, but our design is generic enough that it can actually accommodate any of the 4 designs. But we will just explain it using mode 0. And we'll assume that we're going to be sending 8 bits and the most significant bit is shifted first. Because the slave select signal is not really directly related to the master, even though it's generating it, it's really not that difficult to generate. We're just going to implement it outside the controller in a different mechanism. So we will only focus on the controller's main functionality, which is just shifting in and out data bits by bit. And this is basically what's explored in here. And the other thing that the master controller does is actually it generates this particular clock. Remember, this is not the system clock. It's actually an SPI clock generated by the master. So in order for us to simplify things, we will divide the shifting procedure into 2 parts. We're going to call them part 0 or P0 and part 1, which is P1 in here. So in mode 0, what we saw is the following. In P0, the driver, okay, the controller, basically the master, drives the master out, slave in, basically the MOSI line. It just drives that bit on the MOSI line. And when it does as well, it actually lowers that particular clock, indicating to the slave that it needs to do the same exact thing, which is basically driving its master in, slave out, or the MISO line. Okay, so it's doing a couple of things during P0. So the master, because we're designing the controller, the master controller, it's gonna drive the bit it wants to send on the MOSI line, and it will just lower the clock. It doesn't have to worry about the MISO line because the slave is doing it, but it's indicating to the slave that it needs to do it just by lowering that particular clock. In part 1, which is actually the sampling, what it does, it actually indicate to the S clock or the SPI clock to actually go from 0 to 1, which indicates to the slave that it needs to sample whatever you put on the data data bit on the master out slave in. And at the same time, what it does is actually samples a new data bit from its MOSI, which is the MISO line, basically the master in, slave out, basically whatever happens on the master, whatever the slave actually sent. So P0 actually drives, P1 samples, drive, sample, and we repeat this about 8 times till all the data bits are shifted. And here again, I'm just showing you what's happening in mode 0, but the shifting and driving might basically be different. Maybe in a different mode, the P0 would be the shifting and P1 would be the driving, or the sampling and the driving, so depending on the mode. But anyway, any of the modes will have a couple of parts, part 0 and part 1. And the reason why I'm talking about part 0 and part 1 is because the controller is basically, we're going to design it like a finite state machine. It is a finite state machine, and in that finite state machine, it has, this is the FSM, like basically the ASM chart. It has an idle state, a P0 state, and a P1 state. So it simplifies things. So what do you see in this particular diagram? If you follow it, it's pretty straightforward. So in the idle state, I also have a ready signal, which is an output of the controller that tells me I'm ready to send or receive or do something like that. So you can actually just check it if you want to. And then once it starts, it actually zeroes out a few registers. So C is actually the one that we'll be using to actually generate the exact clock cycle that we want. And the way we do it is actually we compare it to some sort of a divisor, and you'll see it here compared to a divisor. What's the value of the divisor? Well, it depends on the SPI frequency you want. So different peripherals will have different frequencies. So you're going to use this particular equation using the system of clock, the frequency you want. You just do this, and that's basically the purpose of the C register. So the C register in any of the modes, in any of the states, you'll see at the very end of it, before you leave, you're actually putting a 0 in it. You're putting a 0 in it. Like if you're leaving to the next one, not like repeating, because if you're repeating, that means you're just basically inside in here. Okay, so its purpose is just to make sure that it tracks the SPI clock. That's what the C is. N is similar to what we've seen in a previous example of serial communication protocol. It just keeps track of how many bits we send. And in here, you'll see that the question is asking, is N equals 7, basically, whether it shifted 8 bits or whatnot. At least this particular diagram is sending 8 bits. And the last one in here is this register, which is the serial out. It's actually taking whatever is DN is, which is basically 8 bits from the outside. You just load it into the shift register of that controller, which we call it S out, which is serial out. Okay. And you do that. So in P0, again, what you're doing is you're doing a couple of things. You're making sure everything is happening, and then here you will see that it's you're zeroing out that C, and you're shifting. You're basically doing you're driving and sampling and so on and whatnot. And you can actually follow what's happening. And at the very end, we're gonna just issue a very small tick that tells me like I finished. So the implementation of this particular code or this particular diagram is pretty straightforward. So we can go to Vivado and just see it. So it's pretty straightforward. Again, what we have is we have the inputs and outputs. We have a DN that basically it's in 8 bits. This is what we need the master to send. And we have the divisor so that we can have different, basically, so it's actually very flexible. Okay, and then of course we're gonna have a start signal so that we can start all the procedure in here. Okay, and this is what we saw in terms of the ready and the start. And then we have the polarity for the clock and the phase for the clock, and these are actually what's interesting in this code, and this is why I'm stopping in here. It's actually defining the mode of operations that we want and the D out is actually whatever after the tick, that done tick is, that particular value would contain whatever the slave actually sent to the master. And that's basically the tick. It's actually for me, and the ready just to make sure that it's available. And again, I have like these are the basic SPI signals: the clock, the MISO, and the MOSI. You can go through it. It's actually pretty straightforward implementation of the FSM chart, or the ASM chart that we just saw. However, the most interesting thing in it is how it's generating the clock. So I'm just going to focus on it. It's actually generating it in a mechanism we call look-ahead output decoding. So let's take a look at it in a more focused way. Okay, so what we have in here is I'm showing you all of the modes, and again, what we have is we have the P0 and P1. So the look ahead is actually generated in a couple of ways. So let's take a look at the code in here to see it. So we are generating some sort of an intermediary signal, and we call it a P clock, okay? And that signal does the following. It tells me if this next state is P1, so if the next state is P1, the next state is P1, and currently my C phase is actually not asserted. Basically, it's 1. So if this is here and then this is 1, I want the P clock to be asserted, to be on the 1. So let's see what's happening in here. What's happening in mode 0, this is actually what's capturing. It's telling me S clock would be 1 in P1. That's what happens. Look at that in here. So during P1, I need the clock to be in 1. So this one here, it's telling me that if the next state is P1 and the C phase is not 0, okay, which is 1, basically the phase is set to 0, like this one in here, okay, assert that particular clock. So it's telling me if the next one is P1 and C phase is 0, you should assert it, and that's basically what's happening next. Similarly in here, the other mode, which probably is this one in here, which is basically which is mode 1. Okay, it's telling me if the next state is actually P0, okay, which is this one in here, and the C phase is asserted, you should actually raise the clock. So it's telling me you should raise the clock if one case is actually, and the next one is phase 1. It's actually just associating the part 1 with the phase. So they should be opposite to each other, and you can actually see it in the diagram, okay? So whether the phase is 0 and the next one is P1, that's actually mode 1, and the phase is 1 and the next one is P0. And that's why we call it look ahead, because we're looking at the state next, the next state that is coming. And if that's the case, we basically raise the clock. So the more interesting thing is actually the smart part of it is actually how we're actually generating the SPI clock. So in the first line, we just incorporated the phase. We did not incorporate the polarity, but we can incorporate the polarity pretty straightforward, because what we did is we kind of coded mode 0 and mode 1, okay? That's what we coded, and we know that mode 2 is opposite to mode 0 and mode 3 is opposite to mode 1. So all we have to do is just check the value of the polarity in here, and that's what we have. So the polarity, if it's the polarity is 1, what you really need to do is you need to do opposite what we have, because in the polarity that is 1 is actually mode 2 and 3. Other than that, just generate that clock. And this particular SPI clock next is actually not the one that we output directly to the outside world. This is actually registered. So again, we take a look in here, we see this is the SPI clock next. SPI clock next is actually a value that basically is registered to SPI clock. And the reason why we registered it is because we have some sort of a combinational circuit in here, and I just want to clear out all the glitches. So the S clock is actually a register. The same exact thing we did before, which is basically I have a next state and a current state, and actually the current state is what we have. The bottom line is the signal is actually just registered, so we have some sort of a delay, and just to avoid some glitches.